In this topic of complex numbers, we're going to introduce new terms and phrases that you won't have heard of before. And this is one such phrase, and it's called the conjugate of complex numbers. Now, if I go and consider a simple quadratic equation like this one, we can use we can try and solve it by factorizing it, but we can't factorize 7 because 7's only got two factors, itself and 1. And that won't make the number -5. So I'm going to have to use the general quadratic equation. If I do that, I'm going to come up with this solution here. I'm going to get that x is equal to -5 plus or minus the square root of -5 squared minus 4 times 1, the value of a, and times 7, the value of c. So I've got all of that, and we're going to divide all of that by 2 times the value of 1. That's the general quadratic equation, which you should be by now very familiar with. If we tidy up all of that, we're going to come up with 5 plus or minus the square root of 25 minus 28, which is going to give me -3, and that's going to be divided by 2. And normally we would have said in the past that you can't, this thing has no solutions. If we were to draw it, it'd be one of these situations where the graph is going to be intersecting above the x-axis. However, now that we've got complex numbers, we can say actually what we have here are two solutions. We've got this, we've got x is equal to 5 plus the square root of -3 over 2, or x is equal to 5 minus the square root of -3 all over 2. Now that square root of -3, I can rewrite that. I can write that as the square root of -3, square root of -3. I can write that as the square root of 3 times -1. And the square root of 3 I can write as the square root of 3, and the square root of -1 I can write as I. So I get a solution here that I could have x is equal to 5 plus root 3i all over 2, or x is equal to 5 minus root 3i all over 2. And you'll see that we've got two answers. And because of the symmetry that we get within parabolas, you'll see that these two answers look very similar. The only thing that's different is the one has got a plus in it while the other one has got a minus in it. And what we have here is a pair of conjugate solutions, a pair of conjugate numbers that we get with all complex numbers. So whenever we solve a complex equation that's got real roots, we're going to come up with a pair of solutions, and they are called a conjugate pair. And that's what we're looking at in this particular topic. So we're going to look at the properties of conjugates. So if I define a complex number as being a plus bi, then its conjugate pair is going to be z is equal to a minus bi. And we note this down as z with an asterisk next to it. So if I look at adding these two together, I'm going to get a plus bi plus a minus bi, and that will result in a simplified answer of simply 2a, 2 lots of the real component of the number. If I go and take away the number and its conjugate, I'm going to get a plus bi, plus it's going to be minus a minus bi, and the bracket is going to affect both things. So I'm going to get a minus a, which is going to mean the real component will disappear, and I'm going to have bi plus bi, so I'll have 2bi. So the difference between two conjugates is going to be the imaginary component being doubled. If I go and multiply a number and its conjugate, well, I'll get a plus bi multiplied by a minus bi, and that should look familiar to you from the difference of two squares. I multiply the first element, that's going to be a squared minus bi squared, and bi squared, well, I know that I squared, put it this way, I know that square root of minus 1 is going to equal I, so I squared is going to be the square root of minus 1 squared. And so, in fact, I squared is equal to minus 1. So what I have here is, in fact, a plus a squared plus b squared. So that's what happens when I multiply to a number and its conjugate. Finally, if we look at the quotient of a number and its conjugate, we're going to get a plus bi divided by a minus bi. And just as we did when we were working with rationalizing surds, I'm going to multiply top and bottom by a plus bi. In order to make the denominator look a little bit more neat and tidy. So I'll have a plus bi all squared over, now again we should notice that we have here the difference of two squares. So it's going to be a squared, just like we had over here. We're going to get plus b squared. And so the quotient of a number and its conjugate is going to be a squared plus b squared plus 2bi, abi rather, to abi, and I write it like that because this gives me the real part and that gives me the imaginary part, divided by a squared plus b squared. So we can get problems that now relate to conjugate numbers. We can look at these ones here. We want to find the complex number in the form z is equal to x plus I. That satisfies the equation. So we've got two lots of x plus iy minus its conjugate. Its conjugate is going to be x minus iy. And that's got to equal 3 plus 6i. Well, if I tidy this up, I've got two x's, take away one x, it's just going to leave me with x. I've got two iy's, minus a minus iy, minus a minus iy becomes a plus iy, so I'm going to get plus 3 iy, and that's going to be equal to 3 plus 6i. And so if I just go give myself a bit more space here and take that out the way, I don't need that. What am I going to have here? I'm going to have that x is equal to 3, and I'm going to have that y is equal to 2. So in other words, the complex number that I'm looking for is z is equal to 3 plus 2i. The second example, fairly similar. We're going to approach it in the same sort of way. I've got I times x plus iy. And I'm going to take this complex number that I have on the left-hand side and move it over to the right-hand side. It's going to give me 10 minus 2i. Take away 2 plus I. So what have I got on the left-hand side? On the left-hand side, I've got xi plus I squared y is going to equal 10 take away 2 will give me 8. And minus 2i minus an I will give me minus 3i. Now, if I look at the left-hand side, I've got this I squared again. which we've seen before is equal to -1. So I have in fact here got minus y plus xi is equal to 8 minus 3i. Now I've written it in that format because normally with a complex number we have the real part first and the imaginary part second. So if we look at the real part is this part here. So quite clearly we can see from that minus y is equal to 8, and so therefore y is going to equal -8. We can look at the imaginary part. The imaginary part is going to be over here. Those two must match up. So in other words, that tells me that x must equal -3. And so therefore the complex number that I'm looking for is going to be -3 minus 8i. And that's where we'll leave this task for now. We'll come back to more problems on conjugate on equations a little bit later. Goodbye.